Good day and welcome back to the first part of our discussion on line integrals. In this video we're going to introduce the concept of a line integral with respect to arc length. Notationally we're thinking for a function of two variables. We will have a line integral over C of a function ds. And the subscripted C is going to tell us the curve we are integrating over, the function which we are integrating, and the ds is just going to kind of tell us computationally how we go about this integral. And from an intuitive perspective, what we are attempting to compute is how much of this surface sits over the curve C. That is, what is the total accumulation of the function over C? And to set this up, we're going to go through a process that we've encountered previously. We somehow want to break things into pieces, approximate what's happening on a little piece, and then combine things back together. And as usual, I don't want to go through every little detail, but instead just enough to see how things work. In order to set things up, we need a parametric description of our curve. So we're thinking something like a vector-valued function representing the curve. So maybe it's r of t is equal to first component x, second component given by y. And we'll encounter the common curves that we've seen before, portions of circles, something that might be representing just a function of x or y, along with line segments. And in a future video, I'll give a summary of the parametric descriptions that we should be familiar with. And to break up this curve, we need to start by breaking up over the interval of where the parameter t is located. So we're going to take our standard approach. We take this interval from a to b. We'll say a is equal to t naught. And then we break the interval, or divide the interval, up into n equally spaced subintervals, where notationally the first one will be t0, the next point would be t1, t2, t3, and so on. And then in that arbitrary ith interval, we'll think t sub I would be the right-hand endpoint of the ith interval. We finish with b equals t sub n. Now, how this works is that each value of the parameter t is going to tell us an x-coordinate and a y-coordinate of a specific point on the curve. So notationally, we will let x sub I be equal to x of t sub I, and y sub I be y of t sub I. So each one of these parameter values marking the right-hand endpoint of one of our intervals corresponds to a specific point. And I don't want to write down the ordered pair in each case, so let's just call p sub I the point x sub I, y sub I. So for example, that starting point of the curve C would be p naught. The finishing point for the curve would be p sub n. And just so there's no confusion, p sub naught is going to be this point x of t naught, comma y of t naught. Or because you actually know t naught is a, it would be x of a, comma y of a. And the rest of the points are going to appear on here. There's going to be a P1, a P2, a P3, somewhere a PI, a Pn minus 1, all the way up to a P sub n. And an observation you're hopefully making is that I have not spaced these points out evenly on the curve. And that's intentionally. Even though we have equally spaced parameter values, that doesn't mean we travel along the curve at a constant or uniform speed. So these points do not need to be equally spaced. But what we can observe about the points is that they break our curve into n little subarcs. And even though the length of each of these subarcs will not be the same, we could represent them notationally. So n little subarcs of length, let's let delta s sub 1 be the length of the first subarc. So that would be the length of the curve in green. Delta s sub 2 would be the length of the second subarc. So the length of this curve in yellow. And so on. And we now have all of the information we need to define a line integral with respect to arc length. And as mentioned previously, this is represented notationally as a line integral over a curve C of a function f with respect to arc length. And how we define this is we just think about what's happening on an individual little piece. So on an individual little piece, we are thinking that we're evaluating the function at maybe the point p sub I to get a height of something, and then we're multiplying it by a length of the base, so delta s sub I. So how much area does this function of two variables enclose over this small little portion of the curve? Now, working backwards, this is approximating over one little piece, and we have broken the curve up into n little pieces, so we add these quantities up. And what we've seen in the past is that this is something we would call a Riemann sum, and if we were to maybe take the limit as n goes to infinity of our Riemann sum, we turn this into a definite integral. And the definite integral is going to be an integral over how those parameter values vary, in this case from a to b, the function we are integrating, which will be f of x of t, y of t. So that is to know we must substitute in those parametric equations to get everything in terms of t, and then we're multiplying this by delta s sub I, the length of a small portion. And we represent length, much like we did earlier this semester, as the square root of x prime of t squared plus y prime of t squared. And this is the formula that we will use to calculate a line integral with respect to arc length. Now at the top of the next page in the note packet, there's space for an observation, and because I'm dealing with, in a sense, unlimited space on my tablet, I'm going to go ahead and make the observation directly with this formula. Typically, we will refer to this delta s of I portion turning into a ds, and I just want to note that if we have our r of t, the parametric description of our curve, represented as a vector-valued function, then the quantity in front of that dt is a familiar one. In fact, that would be the length of the derivative vector. And this observation is made purely for future reference, as it will come up in our next section. So an alternative way to write this would be to place a magnitude of r prime after the function f. And once again, this is purely for future use. Now, as usual, this process of developing the definite integral is not something I will ask you to recreate, or even something that you truly don't need to fully understand. But there is a kind of base level intuition that we can take from this. And that intuition that we can take away from it is the physical interpretation of what it is that we're calculating. So if we want to find the line integral over the curve C, we're thinking the curve C is this portion sitting in the xy plane of a function f with respect to arc length. So in this case, we're thinking that the upper curve is given by the portion of the surface z equals f of xy. And this allows us to very conveniently interpret the line integral. We can interpret the line integral as the area that's shaded in blue. And how I picture this is I think of the surface as representing the top of a big, long gymnasium curtain. And what we're doing is just calculating the area of that curtain. And the difference is that this function's not going to have uniform height, so it might have ups and downs, but it's still the area enclosed above that curve C and below the surface determined by the function of two variables. Now that we have a formula for calculating a line integral, let's jump into a nice concrete example. Let's evaluate the line integral over the curve C, which is made up of the right half of a circle of radius 1 centered at the origin, of the function xy to the fourth. And in order to set this up, our starting point is always going to be a parametric description of the curve. So of course, if it's possible, we should always draw a picture. And in this case, our curve is made up of the right half of a circle of radius 1 centered at the origin. And from our past experience earlier this semester, combined with our experience from Calculus 2, we should all be able to parameterize portions of circles. The typical parametric description we would have for a circle of radius r, and I'm going to modify this in a moment, would be r cosine t for x and r sine t for y. And for this parametric description, as your parameter value t varies from 0 to 2 pi, you would start off on the positive x-axis and you would go around the circle exactly one time. For our curve of interest, note the radius is 1. So we're going to go ahead and just disregard the r. So a parametric description would be x equals cosine, y equals sine. To be at the point minus 1, that would correspond to a t-value of minus pi over 2, whereas a parameter value of pi over 2 would correspond to the point at 0, 1. And I'll note there's many different ways to parameterize a circle. This is just oftentimes the most convenient way to do so. And a built-in feature of our formula for calculating a line integral with respect to arc length is that regardless of the parameterization that we use, we come up with the same answer. So in this case, note the parameter value varies from minus pi over 2 to pi over 2. Now recall, as part of our formula, we also need to know x prime and y prime, which I usually compute immediately. So in this case, minus sine and cosine. So the line integral with respect to arc length, we take a definite integral over how the parameter value varies, minus pi over 2 to positive pi over 2. Then we substitute in our parametric equations to the function. That is to say, the x is going to be replaced with cosine t, and the y will be replaced with a sine of t. So we'll have cosine t multiplied by sine of t to the fourth power. Then we multiply this by the square root of x prime squared plus y prime squared dt. And note this part that we've added on is ds, which can be represented, as we noted, as the magnitude of r prime dt. And note this works out extremely conveniently for the given example, because sine squared plus cosine squared is just a 1, and we end up with the definite integral from minus pi over 2 to pi over 2 of cosine t multiplied by sine of t to the fourth, which is a very reasonable definite integral for us to evaluate. In fact, I would claim getting it to this point is really the new part of the problem. But even so, it's still important to make sure that we are practicing our integration skills. So just for fun, let's go ahead and evaluate. This would be well suited for a substitution. If we let u be equal to sine, du is cosine. So we have a definite integral with limits of integration to be determined. Note the cosine t dt plays the role of du, and we are integrating simply u to the fourth. In terms of limits of integration, our lower limit, t equals minus pi over 2, becomes our upper limit, sine of minus pi over 2, which is minus 1. Our previous upper limit of pi over 2 becomes sine of pi over 2, which is positive 1. So with the substitution, our antiderivative becomes as reasonable as one could ever hope. The antiderivative is 1/5 u to the 5th for minus 1 to 1. And now substituting in, we have a 1/5 hanging around out front. We replace the u with a 1. Minus sign, replace the u with a minus 1. And recall, minus 1 to an odd power is still minus 1. So 1 minus a minus 1 results in a leftover 2/5. And just to make a few observations, remember this number we get back, the 2/5, does have some physical or geometric significance, something about how much area is enclosed between the xy plane on this right half of the circle of radius 1 and sitting below this surface. And it's actually a net difference of enclosed areas. Another observation I want to make is that in terms of the work that we should show is a picture of our parametric curve, the parametric description, how the parameter values vary, and the derivatives. And then, as usual with the integration, make sure that you are aligning your work vertically using good notation. In our next video, we will investigate what happens if we calculate a line integral with respect to something other than arc length. So stay tuned and take care.